We want to see whether the following series diverges or converges. So we have the sum from n equals 1 to infinity, negative 1 to the n plus 1 over n plus 1. So this is an alternating series, and we see that because it's negative 1 to an exponent. And for an alternating series test, there's three conditions that must be met in order for it to converge. So it has to be positive, decreasing, and the limit has to go to 0. What I mean by positive, here you ignore the negative 1 to the n plus 1, and you only look at 1 over n plus 1. Okay, so the 1 over n plus 1 is positive because we're only looking at values between 1 and infinity. So this is good. And we know that 1 over n plus 1 decreases. It looks something like this, like if you were to graph it. But here we're only looking from 1 to infinity, so that's obviously decreasing. And it does go to 0, so there's a horizontal asymptote there. So all three conditions are met, so therefore we say this series converges. Next example, we have the sum from n equals 1 to infinity, negative 1 to the n over the square root of n. So again, we have to test the different conditions. So we look at 1 over square root of n to see if it's positive. And obviously because, again, we're looking from n equals 1 to infinity, that's going to be positive. Is it decreasing? Well, it's obvious to see that if I plug in n equals 1, I get 1. N equals 2 is 1 over root 2. The denominator is getting bigger. So obviously this is decreasing. So this condition is met. And the limit is definitely going to 0 because if you look at limit as n approaches infinity, 1 over root n. This is basically 1 over infinity, which is just 0. All three conditions are met, therefore this series converges. Okay, next we have the sum from n equals 1 to infinity, negative 1 to the n, times n plus 1 over ln of n plus 1. So this looks very weird, and it's alternating, but n plus 1 over ln of n plus 1, this makes me think that the limit is not 0, and the reason is because n plus 1 is bigger than ln of n plus 1, because a line is, in the long run, if you're looking at a line versus, a log, it looks something like this. It may, it may cross here, but in the long run, all you care about is the line is going to be bigger than the log. So that makes me think the limit is not 0. So let's check this out. So I'm going to ignore the negative 1 to the n, and look at n plus 1 over ln n plus 1. So I get infinity over infinity, so I can just do L'Hopital's rule. Derivative of n plus 1 is 1. The derivative of ln of n plus 1 is 1 over n plus 1 times the derivative of n plus 1, which is 1. So I can just rewrite this as just n plus 1, and this limit is infinity. So automatically this diverges. And I don't have to test the other two cases. Now I have the sum from n equals 1 to infinity, sine of 2n minus 1 times pi over 2. This is also another strange one. It doesn't seem, well, first inspection, it doesn't seem like it's alternating. But let's look at the limit here. I think that will tell us something, because in general, sine alternates between a negative 1 to positive 1, like all those ranges. So if I look at the limit as n approaches infinity, sine of 2n minus 1 times pi all over 2. This, the inside basically goes to infinity. So sine will always alternate between negative 1 and 1. And there won't be a nice limit that it won't approach a nice number. It's always going to be bouncing back and forth. So the limit does not go to 0. So technically the limit doesn't exist here. And so this series diverges. Okay, last one. We have the sum from n equals 1 to infinity cosine of n times pi. Yeah, this one, again, I'm going to look at the limit because it doesn't seem like it's going to work out. Because cosine oscillates, again, and this will not go to 0. Same argument as the last problem. So this diverges.